service, and it exposes endpoints with a lightweight protocol. Microservices has numerous advantages, such as independent development and deployment, easy horizontal scaling, better fault isolation, and enabling use of different technologies per service. Besides these advantages, it also comes with a cost. Since microservices work in a distributed architecture, it will require to use correct patterns and tools for managing the services and for communication and transaction management between these services. In the coming points, we will focus on the architectures and patterns that will help to solve these problems. Clean and hexagonal architectures. These architectures help to develop and test the business logic of a software independent of the infrastructure, such as databases, message queues, or any runtime tool or device. Clean architecture principles will help you develop long-lasting applications that are easily adaptable to any new technology. In this course, while implementing each microservice, you will be applying the clean and hexagonal architectures. The hexagonal architecture, also known as ports and adapters, and is invented by Alistair Cockburn in 2005. It basically relies on defining well-defined interfaces, which are called as ports, and implementing the interfaces with replaceable adapters. There is also an architecture called onion architecture, which has a similar structure with hexagonal architecture, and both has the idea of isolating the domain logic from the outside dependencies. The clean architecture proposed by Robert Martin in 2012 covers a clean architecture in detail, including the concepts of hexagonal architecture and onion architecture, but also adding the detailed definition on the implementation of the domain layer. Clean architecture uses the principle of dependency inversion to strictly follow the dependency rule that only allows an outer ring point to inner ring and never the other way. I will explain the details of these architectures in the coming lectures, and most of the time, I will use the terms clean and hexagonal interchangeably. Domain-driven design. In each microservice, when implementing the business logic, you will apply the domain-driven design principles. It basically provides some strategic and tactical patterns that help you to implement your domain logic in a way that's easier to understand, develop, and maintain. You will learn and use entity objects, aggregates, value objects, domain services and application services, and also domain events to create notifications for the other services that run on different bounded contexts. Kafka. For the patterns like Saga and CQRS, when you follow event-driven approach, you will need to use a message bus to use an event notification. I will use Kafka for this purpose, which is resilient as it holds the data in persistent disk store, and it is scalable thanks to the internal partitioning strategy. I will mention more about Kafka in the coming sections, but to summarize, Kafka is the concept of topics to store the data, and it provides producers to publish the data on Kafka topics and consumers to read the data from the Kafka topics. I will use Kafka in the implementation of Saga, Outbox, and CQRS patterns. Saga. Invented in a publication on 1987, Saga is used for long-lived transactions. You will learn how to apply Saga pattern to accomplish a distributed transaction across multiple services. The idea behind Saga is to create a chain of local ACID transactions to finalize a long-running transaction across services. For example, as you will see in the next lecture, in this course, you will have a food ordering application that has order service, payment service, and restaurant service. To complete a food order, the application will need a successful payment as well as a restaurant approval. For this scenario, I will implement the Saga pattern using Kafka as the event bus and let the services communicate using events with choreography approach. There is also orchestration approach to implement Saga pattern that uses an orchestrator to drive the Saga. I will use choreography using events. However, I will still use the order service to coordinate the Saga pattern, as you will see in the implementation section. You will see that in the choreography Saga solution, there is no need to use a framework such as Eventuate or Axon. So I will show using a choreography-based Saga based on events using Kafka without additional framework. Outbox. As mentioned in the Saga pattern, when you have multiple services involved in a long-running transaction, how will you accomplish consistency? Think like this. You have two services, so you have two local transactions to accomplish a Saga. First service does some local ACID transaction and publishes an event to notify the second service. Second service listens the event and does its local ACID transaction and publishes another event. Then read and write parts of your system separately and allow to read your data more effectively. This is because you can use different data stores for read and write parts. For example, say you use a relational database for your write database, and you send your data asynchronously to Elasticsearch. Then you can use this Elasticsearch to query your data more effectively. Besides, it will allow you to scale your read and write systems separately. As a natural result of a distributed system, again, this pattern will end up with eventual consistency. Because after you put your data on write database, there will be some delay until your data ends up on the read database. Note that the same outbox pattern should be used with CQRS pattern also, so that you can be sure your local transactions and publishing event operation runs in a consistent manner. Kubernetes and Docker. Kubernetes is a container orchestration system that automates deployment, scaling, and management of cloud-native applications. It allows to run Docker containers while reducing operational complexities. You will learn to containerize your services and first run them locally using Docker. Then you will create. Hi everyone. In this lecture, I will explain the project overview and go over the application components that you will implement in this course. So I will go to Excalidraw website and use it to draw the diagram of our project. First of all, this project will be which will be Kafka, like Postman. I will send HTTP post requests to order service to create an order. The request body will be in JSON format. Here you see the example JSON request. When I implement the services, while calling the order service from Postman, I will use this input JSON data. As you see, I have customer ID, restaurant ID, address, price, and order items that has the product details. As a response, order service will return tracking ID and status of the order. An order will be created in the pending state. Later, clients will be able to query order service with HTTP GET endpoint and get the latest status. When the order starting to process, the order status then it will have the messaging component to communicate with Kafka. And finally, it will have the business logic for a payment operation. Next service will be the restaurant service. This service will approve an order by checking some business logic like availability of a product. It will again have the data access, messaging, and business logic. The last service is the customer service. At the start of the course, I will use a materialized view in the customer database that will be populated with a trigger on customer table. And I will let the order service to query the customer data directly from the customer's key here. The services will produce and consume events to communicate each other. And they will use Kafka to send and receive these events. First of all, to complete an order process, to create the order in the local database. So I will set number 1 on the order service local database to indicate that it is the first step. Then it will send the order created event to the payment request topic. So this will be the second step. Then payment service will listen this topic. So this will be the third step. And then it will process payment in the payment database, which will be the fourth step in the order processing. Then it will create a payment completed event on the payment response topic. And this is step 5. Finally, order service will consume the payment response topic and update order status as paid in the order services local database. So the message listener will be step 6, and the database updates on the order service will be step 7. As you see, the order service local database is updated twice up to now, in step 1 and step 7. Then, to get an approval from restaurant, we will need another 2 Kafka topics. Restaurant approval request and restaurant approval response. Order service will request an approval by creating an order paid event on the restaurant approval request topic. This is step 8. Then restaurant service will consume this topic with step 9 and process approval of order in the restaurant database. This will be step 10. And then it will create restaurant approved events on the restaurant approval response topic, which will be step 11. Finally, data flow of an order process. This picture and steps actually the baseline for Saga pattern implementation. Here, one thing to notice is that the order service acts as a coordinator for the Saga flow because it initiates the Saga, then gets payments completed event, and then asks for approval to the restaurant service using the get endpoint. And after that, the client can trigger the next step, such as the delivery process. Callback method in each Saga step. And later, when we implement the Outbox pattern together with Saga, we will also track the Saga status and Outbox status next to order status. Alright, current picture has almost all the components that you will implement in this course, but this picture is far from complete. To complete it, we need a clear architecture with a well-defined domain logic, and also we need to cover failure scenarios for Saga and CQRS patterns. So let's start improving this architecture. I will do that in the next lecture. Alright, let's continue by improving the project architecture. The first thing I will add to this project will be hexagonal or clean architecture. This architecture, also called as ports and adapters. Basically, each microservice in this project will follow the clean architecture principles. In the next section, I have a separate lecture to go into details of this architecture. But basically, with this architecture, you will isolate your domain logic from infrastructure and outside dependencies. This will be achieved by separating the service into different deployable units. As you see, here I have different boxes for each of the components, and it implies that I will have different modules for each of them. So each of the layers, data access, messaging, REST API, and business logic, should be deployable separately. And this requires to have different deployable units as components, as you will see in the implementation section. The next step is to define input and output ports of your domain logic. So please note that all input and output ports that are interfaces are defined in the domain module. So here I will draw input ports and output ports for order service. These ports are nothing but interfaces that need to be implemented by adapters. So I will have some adapters in this architecture. The first adapter type is called as primary adapter, which is the HTTP client in this picture, and it will call the domain logic. Domain logic will implement the input ports, and these input ports will be used by the REST API. So if you think the data flow, I will call the order service REST API from Postman, and it will first hit to REST API component, which will have a controller class. Then it will use the input port that is defined in the domain logic and call the methods exposed by this input port. To use the input port, REST API module will have a dependency to the domain module. Then it comes to the secondary adapters. These adapters will implement the output ports that are again defined in the domain layer. The data access and messaging components will have these secondary adapters. Now, if we continue data flow, after getting requests from clients and calling the domain layer methods, we will process the business logic, and after that, we'll use the output ports to call data access and messaging layers from domain layer. As I mentioned in the next lecture, you will see more detailed explanation of this hexagonal architecture. For now, I will add the same input and output ports to the payment and restaurant services. And also I will mark the primary and secondary adapters in those services. The second improvement to this project will be applying domain-driven design principles. So in the domain logic, I will apply strategic and tactical domain-driven design patterns and use aggregates, entities, value objects, domain services, application services, and domain events. Again, there is a lecture to discuss domain-driven design in detail, but to summarize, an aggregate is a group of business objects which always need to be consistent. These business objects are called entities. The core business logic will be handled in an aggregate through entity objects. Value objects are used to define simple immutable objects with domain-driven names. They don't have identifier and only contains value. An example is having a money object instead of keeping a big decimal Java type directly. Domain services are used to handle business logic that spans multiple aggregate routes, and the logics that cannot fit into any entity by nature. An application service is the point of contact to the outside of domain, so any other layer that wants to communicate with domain layer needs to use application service. Finally, domain events are used to send notifications to other services that runs in different bounded contexts. For example, in this picture, the domain logic in the order service will create an order created domain event and send it through payment service using Kafka topics. Here I will also write down the patterns that you will be implementing. Saga pattern, as mentioned, will have process and rollback operations. And rollback methods are used to handle compensating transactions. We need to combine Saga with outbox pattern to obtain a consistent solution. And I will be using pulling outbox table with a scheduler and keep the state of Saga, outbox, and order in the outbox table for each microservice. With the outbox pattern, I will add a local outbox table to the same database that a microservice runs. Then instead of publishing an event directly, I will first save the event into this outbox table. To save into this outbox table, I will use the same ACID transaction that the order service uses for the local database operations. So I will be sure that the event is created automatically within the local database using ACID transaction. The next step will be reading the events from the outbox table and sending them to the message bus. To do that, I will use pulling outbox table using a scheduler. The same architecture applies for payment service and restaurant service. So I will have schedulers in each service that reads the events from the outbox table. Also, I will make sure that the scheduler will mark the events as sent if and only if it can successfully send the events to Kafka. We will see the details in the implementation section. The outbox pattern will help to cover failure scenarios, such as ensuring idempotency using outbox table in each service, preventing concurrency issues with optimistic logs and database constraints, and updating Saga and order status for each operation. I will make this text smaller to open some space. Hi everyone. In this lecture, I will go over the step 17, and for this, you may go to oracle.com and download and install the latest if Java Home environment variable set correct. First, check the JSON and Maven, and check the Maven version. Go to docker.com and install it. So you may prefer to install Docker Desktop 3 first, which is an image on. I also need to install Docker Compose, as I will be running multiple containers in a single Compose file. So for this, we can go to docs docker compose install link to install the Docker Compose. Actually, with Docker Desktop, Compose comes automatically, as explained here. And finally, I will check the version again using Docker Compose version command. Great, then I will install Postman to use it as a REST client in the application. I will go and download it from postman.com. I will show how to use it while testing the application in the following sections. Finally, to check Kafka cluster and Kafka topics, I will use Kafka Cat and Kafka Tool. You can install Kafka Cat as described in the GitHub page. For new versions, it is renamed to KCat, as you see here. Again, I will show how to use it while examining the Kafka cluster and topics in the following sections. And for Kafka Tool, I will go to kafkatool.com and download and install it. It is a GUI application for managing and using Apache Kafka. So I will be using it to examine Kafka cluster during the implementation sections. Next, please download and install Postgres in your system, because we will use it as a local database for microservices. So go postgresql.org download page and install the correct Postgres version for your system. Also, to manage and view the database tables visually for PostgreSQL, you may install pgadmin from pgadmin.org. All right, so after setting up the environment, let's continue with an introduction to clean and hexagonal architectures in the. Hi everyone. To access the source code of the code, you can navigate to different branches to get the final complete code, or the code before making changes in each section, such as before Saga and before Outbox changes. In the food ordering system infra repository, you can find the infrastructure-related resources to deploy the services of the system into local Kubernetes using Docker, and also the resources to deploy the services into Google Kubernetes Engine. You may also download the source code as a zip file at the start of each section, starting from the section 3, as you can see here. In the next lecture, I will start with explanations of clean architecture. In the next lecture, I will start with explanations of clean architecture, diving into the code. In the next lecture, I will start with explanations of clean architecture and hexagonal architecture, and then design the components of the system. Then we will create the modules of the order service using clean and hexagonal architecture principles. So I will see you in the next section. Hi everyone. In this lecture, I will make an introduction to clean and hexagonal architectures. Basically, by separating the layers and putting the domain layer on the center of the software will lead to a clean architecture. This can be achieved by creating a dependency rule that leads to only allow pointing inwards towards the domain layer. For this, we can use dependency inversion principle and polymorphism to invert any dependency relation. In the next lecture, I will design the components of the first microservice, order service, and show how to apply these principles. In the end, you will have an easily testable software that is independent of any external element. Clean architecture also explains the details in the domain logic and mentions about the entities to implement the critical business rules and use cases to implement the application-specific business rules. In the end, clean architecture can be thought of an umbrella that covers the concepts of hexagonal architecture and onion architecture by adding the details about the core domain logic. All these architectures concentrate on isolating the domain layer and making it the most independent and stable component. The details will be just interchangeable plugins for the domain layer. To explain the component relations, I will now go into the hexagonal architecture details. Hexagonal architecture is also known as ports and adapters. The main idea is to divide the software into two main parts, insides and outsides. The insides will be the domain layer that holds the business logic. This part will be developed first, and it will not depend on any other layer. So it should be the most independent and stable layer, as it is the heart of your software. The outside will include all the dependent layers, such as API that is called by end users, databases that is used to persist the results of business logic, a message queue or event store to send notifications to other systems, an external service that needs to be called from the business layer, or even any framework that is used in the software, such as Spring Framework. All of these outside parts are not actually your software. They should be behaved as plugins to your software. So the main principle of hexagonal architecture is to isolate the domain from any of these dependencies. It will end up with easily testable applications with isolated business logic from the infrastructure and data sources. Hexagonal architecture is invented in 2005 by Alistair Cockburn. He described it as allow an application to equally be driven by users, programs, automated tests, or batch scripts, and to be developed and tested in isolation from its eventual runtime devices and databases. Here you see two types of adapters. Adapters are the interchangeable components. Primary adapters are the ones that use the core logic that is in domain layer. They use the input ports to call the implementations that are defined in the domain layer. While the secondary adapters are implemented in the external modules, like database or message queue. In this architecture, user input is processed by one or more primary adapters and passed to the core logic, and the core logic interacts with the secondary adapters only. Then output of core logic will return to the end user using primary adapters again. Realize that we use interfaces on input and output integration, and dependency injection is used to pass the implementation of the secondary adapters to the core logic, and primary adapters to the outside, such as API. There are numerous advantages of using clean and hexagonal architectures. First of all, you should understand that it is good for... Hi everyone. In this lecture, I will start designing the first microservice that I will implement which is order service. I will use hexagonal architecture and clean architecture concepts before implementing the service. To show you the components clearly, I will use Excalibur website and create the design diagram. So let's start with a traditional 3-layer approach. I will first put the API layer. In this layer, we will have the REST controllers that will serve to an user interface. So here, there will be some kind of a REST client or user interface. Then I will have the domain layer. In this layer, there will be the business logic of the application. In the layers approach, each layer will depend on the next layer. So I will put a depends arrow from API layer to domain layer. Then I will put the data layer, which has the implementation of data source operations. So it will communicate with a data source, let's say with a relational database. Following layered approach, business layer will depend on this data layer. As you can see in this picture, if I want to change the data layer to use another data source, it will directly impact the business layer because business layer depends on the data layer. So any change on the data layer will require the implementation of the interface that is used in business layer. How can I run both business layer and data layer together? For this, I will use another component. I will call it as container. To make this concrete, if you think it as a Spring Boot application, this will be the component that has the Spring Boot main class. In this component, I will have a dependency to business, data layer, and also to API. So when I run this Spring Boot application, it will have all components as jar files, so that the data layer interface will find its implementer in the data layer at runtime. This is the main principle on a clean architecture. We use dependency inversion and polymorphism, and then apply dependency injection to use an interface at compile time, which will have the implementation class at runtime. While writing the order service, you will see that even though I use dependency injection, I will not add Spring Framework dependency and annotations into the business layer classes. So the core logic will also be independent of any framework. I will accomplish this using a bean registration class in the container module. Here we have defined the output ports and the implementer of that ports as secondary adapters. In a clean architecture, we should also define the input ports in the domain layer. I will name this input port as domain layer port here. This port is also an interface when we think it in Java, and it will require an implementer, and it will be implemented in the domain layer itself. So I will add a domain layer implementer in the domain layer. So who will use this input port? As it is obvious, the API layer will inject and use the input port using dependency injection. And at runtime, the method calls will be delegated to the implementation, which is in the domain layer. In hexagonal architecture terms, the API layer that uses the input port is a primary adapter. It is an adapter because it can be easily changed without touching to the domain layer, thanks to the usage of the input port. Remember that the data layer adapter in the data layer was a secondary adapter in clean architecture terms. Let's extend this picture with some other possible components. Let's say you need to have an external service call in business layer. So I have an external service here. According to the clean architecture principle that I just applied, how can we integrate this external service into the application? Again, I will add a port into business layer. This time I will call it as external service port. And then implement it in the external service with an adapter, which is a secondary adapter in hexagonal architecture terms. I will also add the implements arrow from the data layer adapter to the data layer interface to make it clear. Then I will add a messaging component. Again, applying dependency inversion principle, I will add a messaging port interface in the business layer and implement it with a messaging adapter in the messaging component. Let's say this adapter will use Kafka. However, as mentioned, when you want to change the adapter with any other messaging technology, it will be a painless operation, thanks to the clean architecture that you use. So in future, you can easily change the message bus from Kafka to any other solution. In the end, the core logic will be the most independent and stable components in this application, and it will allow to develop and test the business logic independently. So here you see the order service components designed using clean architecture. All right, in the next lecture, I will start implementation and create the modules of order service using clean architecture in IntelliJ. So I will see you in the next lecture. Hi everyone. In this lecture, I will create the food ordering system project and then create the modules of the order service using clean architecture. So let's open the IntelliJ Community Edition that we have downloaded in the setup section. I will first create a new Maven project, food ordering system. As group ID, I will use com food ordering system. And as artifact ID, I will use food ordering system. I will click on Finish button and create the project. If I open the POM.xml file, you will see the group and artifact ID. And also you see the Maven compiler source and target set as 17 automatically. This will be the main project, and I will create the services and modules under this project. So there shouldn't be a source folder here, because I will not put any Java source files in this folder, so I will delete it. Then I will open POM.xml file. Here I will use packaging property to set this project type as POM. Here we can use two types of packaging, POM or jar. The default one is jar, and it will create a jar file from the module. For the main project, it doesn't make sense to use a jar packaging, as there is no source code. So I set it as POM here, and make it the parent POM.xml file for the child services and modules. Parent tag version, which is property as file system for parent Maven projects. But since we have an external parent project, which is Spring Boot, we don't need to search local file system. The parent POM will be loaded from the Spring Boot library. If your parent is an external project, is a best practice if your parent is an external project like Spring Boot. To keep the versions in a single place, I will create a Maven compiler plugin file. I will also create a Docker image from that runnable jar and run it on a Docker container. So that's why I named this module as order container. So let's create this module, order container under order service, again as a Maven module. I will remove the auto-generated Maven compiler property from all the two more submodules to separate the core domain from the application services, which are the services that expose domain methods to the outside. So let's go to order domain and first create a new Maven module named order domain core. Choose order domain as the parent for this submodule and click on Finish. I will put the core logic in. Click on Finish. I will put the core logic inside this module. So this will include. I will remove the Maven property. Hi everyone. In this lecture, I will set the dependencies between the order service submodules. Let's start with order domain core. Which dependencies should I add here? Yes, that was a trap question. I should not add any dependency in the core domain because it should be the most independent and stable component. Hi everyone. Let's make an introduction to domain-driven design. After this introduction, in the next lecture, I will start implementing the domain logic of the first microservice, which is order service. Domain-driven design is an approach to software development that centers the development on programming a domain model. It is especially useful to build systems that have a complex business domain. The main idea is to separate the business model from the infrastructure. If you have already watched the Introduction to Hexagonal Architecture lesson, you should have caught the similarity. Both hexagonal architecture and domain-driven design put the domain logic in center of the software and makes it independent of the outside world. Separating domain logic and infrastructure makes the software easier to design, develop, test, build, and maintain over time. It will keep the domain logic stable and help you to change the infrastructure components and adapt to new technologies easily. There are two sides of domain-driven design, strategic and tactical. Strategic domain-driven design focuses on boundaries in a domain model and introduces the bounded context idea. Domain itself is the operational area of a system, for example, a food ordering application, and it should have well-defined boundaries within that domain. These boundaries are defined using the bounded context, and it will help to group the functionalities of a system. A domain can have one or more subdomains depending on the domain logic. The next important concept that strategic domain-driven design brings is the ubiquitous language. It basically defines a common language between domain experts and developers, so that the system can be designed, developed, and evolved with a well-communicated environment with the contribution of domain experts and developers. The tactical domain-driven design, on the other hand, focuses on the implementation details of the domain logic. Let's start with entities. Entities are the core domain objects. They have the critical business logic. An entity must have a unique identifier that is assigned to an entity when it is created, and it remains unchanged throughout the lifespan of the entity. Two entities with the same identifier considered to be the same object, even if all other properties are different. Likewise, two entities considered to be different if their identifiers are different, even if all of the other properties are same. Entity objects are mutable objects, as it will run some business logic and update the properties based on the calculations. However, it shouldn't mean you should create setter methods for every property of an entity. It should have state-changing methods with well-defined names by using the correct verbs. The second concept is aggregates, which is a group of entity objects that are logically related. For example, you may have an order process aggregate that includes order, order item, and product entities. The important thing with an aggregate is that it should be retrieved and stored as a whole in a consistent state. This requirement brings us to the next concept, aggregate root. An aggregate root is responsible to keep the aggregate in a consistent state all the time. So an aggregate is owned by an aggregate root, and the identifier of the root also identifies the aggregate. Aggregate root is responsible to enforce business invariants. Hi everyone. In the next lecture, to bring context to the values. So for the order ID, I will create an order ID value object and hold an UUID field inside this. Let's create a separate space for value objects and show the order ID class there. Since a customer will create this order, I will also add customer ID field. For this field, I will again create a value object and hold a UUID field. Then I need to relate the order with the restaurant that the food will be sent. So I need also restaurant ID. This will be again a value object with an UUID field. Then I need the delivery address. For that one, I will define a street address field and create another value object for that. In street address, I will define 4 fields: UUID ID, string street, string postal code, and finally string city. Next, I need to keep the price of the order, and for that, I will use another value object named money. Inside the money value object, I will keep a big decimal amount field. Then I will have the list of order items, so I will need another class order item, and this order item will be another entity. Let's put the relation arrows for order and order item to the order processing aggregate here. In the order item, I will add first order item ID fields as a value object. For this, I will create the order item ID value object. Then I will add order ID field to relate the order item with the order. The third field in the order item class will be product fields to relate the product information with the order item. This product class should be another entity as it represents a business object with a unique identifier. In product entity, I will put string name and money price fields. In the order item, I will also add integer quantity, money price, and finally money subtotal fields. So basically, quantity multiplier by price should give the subtotal for an order item. Great, now I can return to aggregate root order. After adding order items, I will also add a tracking ID using another value object. This tracking ID will be used to query the order status, so we won't need to expose the internal order ID field. I will use UUID for the tracking ID value object. Then I will add order status value object. Then I will create another package here, named here in the money value object. First, I will add public is greater than 0 method with return type Boolean. Here I will check if the amount is greater than 0. First, I will check if it is not null and use compare to method on amount object, which is big decimal. Then I will compare it with big decimal 0. Notice that I used compare to methods here instead of equals method on the big decimal object. If you use equals methods, and if you have a big decimal with decimal points like 0.00, and you use 0 integer in the comparison, it will not return the correct result. So by using compare to method, I will be sure that the comparison return the correct result, whether my value has decimal points or not. So it's a best practice to use compare to methods for this type of comparisons in the big decimal operations. Now, as you see, I have 4 additional public methods that I decided on the design. These methods are the state changing methods to change the state of an order during order processing. So basically, these methods will help me to create a simple state machine to validate the previous state and apply the next state. Let's check these states and the transitions on the project diagram. When an order first initialized, it is in the pending state. Then it will go to the payment service. Payment service can return 2 responses, payment successful or payment failed. If payment is successful, order should transit into the paid state. So in the pay method implementation, I should first check if the order is in pending state. If not, throw an exception. And then I will set the order status as paid. Let's implement the approve method next. If payment returns successful and order status set as paid, this paid order will send to restaurant approval. If approval is successful, order should go into approved state. For this case, I first need to check if order is in paid state. If not, throw an exception. And then set the status as approved. Next method is init cancel. Let's check the project diagram again. If the restaurant approval fails, order is in still paid status, right? In that case, to create a consistent application, order service needs to inform payment service to roll back the payment operation. In that case, I should set the order status as canceling and send a cancel request to the payment service. Please note that I will cover this scenario while implementing Saga pattern, as this is an example of compensating transaction. So what should be the current state for init cancel operation? It should be in the paid state, as the payment should have been done already. If this is not the case, I will throw an order domain exception here. Then I will set the order status as canceling. Finally, the cancel method. For this one, order could be in 2 different states. First one is pending state. If the order is sent to payment service and payment failed, I should set the order as cancelled. In that case, the current order status will be pending. There is another state that could lead to cancel state. That one is the canceling state, as mentioned. In case of approval is failed, order is set as canceling, and the payment service is called for rollback operation. When payment service completes the rollback for the payment, order service should set the order status as cancelled. Hi everyone. Let's continue with implementation of domain service. I will create order domain service input class. and implement order domain service interface. In the validate and initiate order method implementation, first, I want to validate restaurant with a validate restaurant method. I will pass the restaurant object as parameter. Let's create this method. I will implement it shortly. Then I will create a method called set order product information and pass order and restaurant information. Remember that in the order item, we have a reference to products, and this product entity has name and price. I put that entity in order item just to be able to check the real price of a product. Remember that I get the product ID and the item price from the client, from the customer. But to be sure that this price is really the price of the product, I will get the product information from the database using restaurant entity. And then I will cross-check the product information here. I will implement this one shortly right after implementing the validate restaurant method. Here you see that the domain service uses multiple aggregates to check some business requirements. Then I will call validate order methods on the order object, and then call initialize order methods again on the order object. If everything goes correctly, I will then return an order created event and pass order and current time with UTC zone as the parameters. I use zone datetime now method here and use the zone ID of method to use UTC zone. As you may know, UTC stands for Universal Time Coordinated, and it is the primary time standard by which the world regulates clocks and time. Great, now before implementing remaining methods, I want to add logging in this class. And this will be the only place that I will use a library in the domain module, but only in the domain service, not in the domain core. I will go to base PAM XML file and add provided Lombok dependency, and also Spring Boot starter logging dependency in the dependencies section. Here I use dependencies section instead of dependency management because I will use these dependencies application-wide, even in the domain service. Then I will add SLF4J annotation to the domain service implementation. After Maven reload, the annotation should be available to use here. And then I will simply use log info methods to log information before returning from the validate and initiate order method. Now in the validate restaurant method, I will simply check if restaurant is active using the Boolean property on the restaurant entity. If it is not active, I will throw an order domain exception here. Then in the set order product information method, I will get the order items and use for each method. Then I will use the current order item as the input to the lambda definition in the for each method. And on the implementation, I will get restaurant product and use another for each, this time for the restaurant products. Then I will get the current product for the order item and find the corresponding product in the. Hi everyone. In this lecture, I will make an introduction to Kafka. As mentioned previously, I will use Kafka in the implementation of Saga, Outbox, and CQRS patterns, and keep the domain events in Kafka to trigger domain event listeners. Let's see the high-level architecture of Kafka. Kafka brokers are the servers that forms a cluster and serve to producer and consumers to insert and read data. Having multiple brokers in a cluster is important for high availability, because with multiple servers, Kafka can replicate the data on different nodes and increase resiliency of the system. Kafka has the concept of topic, which is a logical data structure that consists of partitions. And partitions are the smallest physical storage unit that holds the data. As mentioned, some data can be replicated on different partitions on different Kafka brokers to increase resiliency. This is achieved using the replication factor property. For example, if Kafka cluster has 3 brokers and replication factor is 3, then the same data will be replicated on 3 different partitions on 3 different nodes, and this will provide a strong resiliency. Producers write data at the end of a partition, and consumers read the data from the start of a partition, and keep an offset with an ID to continue from the offset in case of restarts. Consumers achieves to read the data from the offset using a consumer group concept. So a consumer belongs to a consumer group, and a consumer group will not read the same data more than once. Instead, it will keep reading the new data using the offset. One thing to note here is that if you create a new consumer group with a new identifier, you can read the data again from the start of a partition. Kafka has two important features. One is the resiliency. As mentioned, resiliency is achieved using a replication factor and duplicating the same data on different partitions on different broker nodes. The second important feature is the easy scaling. You can have parallel consumer threads up to the partition number in a topic. That means if you create a new partition, you can create a new consumer and consume the data with a new thread concurrently. Finally, as mentioned, the data is inserted as an append-only lock into the partitions. And once inserted, the data cannot be changed or updated, so it is immutable. Since it inserts data to the end of a partition, it is fast. There is no need to search the place to be inserted. And if you want to see a final state of a record, you can get the history and calculate the latest state. Or you can use a K-table using Kafka streams and hold the latest states in a table-like structure and query it anytime. All right, let's also discuss the other components that are used in running Kafka. Currently, in production applications, Kafka still requires Zookeeper to manage the cluster and hold the metadata. There is KIP 500 mode that allows to use one of the Kafka brokers as the orchestrator. This will allow removing Zookeeper dependency, but it is still not in the production-ready state. There is also schema registry component that has. Hi everyone. In this lecture, I will run a Kafka cluster using. I will put the source code of Kafka producer and consumer here in the next lectures. Let's delete the source folder as I won't use this module to create Java source files, such as hostname, schema registry listener, Zookeeper URL, and Bootstrap servers. Again, I use Kafka version and global network variables from environment file. In Kafka brokers, I use Confluent Kafka Docker image using port 19092, and I set the environment variables like Zookeeper address and listener names for the Kafka broker. As you see, this broker is accessible using Kafka Broker 1 hostname with port 9092. And also from outside of Docker, it is accessible partitions in 3 different brokers. Since I already created 3 Kafka brokers in the cluster. Hi everyone. In this lecture, I will create the generic Kafka producer and consumer modules to use them from the microservices. So let's go to the infrastructure module and create a submodule, Kafka. I will delete the source folder and create a submodule, Kafka, producer and consumer modules to use them from the microservices. So let's go to the infrastructure module and create a submodule, Kafka. I will delete the source folder under Kafka module. Then I will create 4 Maven submodules. Kafka producer, Kafka consumer, Kafka model, and Kafka config data. As you see, I choose the Kafka module as the parent for all of those submodules. First, I will go to POM XML file of Kafka module and be sure that the packaging is POM, because this will be the base POM for the sub-Kafka modules. Then I will add Confluent repository with a repository section, because I want to use Kafka Avro serializer dependency from the Confluent library, which is not in Maven central repository, so I need to use Confluent repository for that. I will create a dependency management section here and define the dependencies with versions in this base POM XML file, so the submodules will be able to use these dependencies without setting the versions. Here I define Spring Kafka dependency with version 282, I'll also add Kafka Aura serializer dependency from Confluent with latest version 7.0.1. Finally, I will add. Hi everyone. Hi everyone. In this section, I will complete the order service with all components and modules. Let's start with order application module, which will include a REST API. I will first go to PAM XML file of order application module and add Spring Boot Starter web dependency. This dependency will bring the required libraries to implement a REST API. I will also add Spring Boot Starter validation to implement data validations. As you see, I already have order application service dependency to use the input ports of the domain layer in this REST API. Let's create a package, com food ordering system order service application, and create two subpackages, REST and exception handler. In the REST package, I will create order controller and annotate this class with REST controller annotation, which will simplify the creation of REST API. I will also use request mapping annotation and use mapping orders with application VND API v1 plus JSON response type to indicate that this is a JSON API. Let's also add SLF4J annotation to add a log variable automatically. In this controller, I want to forward the client request to the domain layer. And as you remember, to communicate with domain layer, I have to use application service interface, which is the input port in hexagonal architecture terms. I have already a dependency to order application service module, as you can see here. So I will create a field. Hi everyone. In this lecture, I will make a short introduction to CQRS pattern. CQRS stands for Command Query Responsibility Segregation. It basically relies on separating the write and read components in a system. This will enable scaling both parts separately and also enable using the correct technology or data store for each part separately. This leads to an eventual consistency because the read part will be updated asynchronously with a small delay. Eventual consistency is a concept used in distributed systems and is actually the natural result of having distributed services. If you can accept this type of consistency, it will enable highly scalable systems. In this picture, you can see the command and query parts of a system separated clearly. UI calls both parts separately and only gets data from the query store. As you see, the data is updated into read store only after write store is persisted. And as mentioned, this leads to an eventual consistent system. With CQRS, after persisting the events in write database, usually an event is created and sent to event store. In our example, after saving the customer object in customer local database, I will create and send a customer created event into Kafka to hold the event. Then I will consume that event from order service and create my query store for the customer data, specifically in the order service. Actually, after putting your event in the event store, you can replay that event many times and create multiple query stores. For example, you can pull your events and create data on Elasticsearch, or create data on an analytics database to run some calculations. So once you create your events separately, you will have infinite chances to consume and replay the events based on your requirements. This is the power of separating write and read parts, and it can be achieved using CQRS pattern. Great, let's start implementing CQRS pattern by changing the customer service in the next lecture. In this lecture, I will start updating the customer service and create the modules to enable creating of a customer through a POST API. In the end, I will have the same clean architecture in customer service as in the other services. So I need to have the domain layer and the infrastructure layers to implement the input and output ports that are defined in the domain layer. Now in this lecture, what I want to achieve is to create a duplicate customer table in the order service. Remember that I had the customer table in the customer service, and I was using a materialized view to serve the customer information. And in the order service, I was using a database call to this materialized view, which is in customer service database. So for this, I had the customer schema defined in the JPA entity definition, as you see here. Instead of doing this cross-database call, I will make a call to local customer table in order service. But to do that, I need to keep this customer table up to date when customer table in the customer service is updated. To achieve this, I will use CQRS pattern, and while updating customer information in the customer service, I will publish an event in a new Kafka topic, and then listen this event from order service to insert the new customer information in the order database. Therefore, I need a new Kafka topic, and for that, I will go and update the init Kafka YAML file in the infrastructure module. I will add a new statement to create a new Kafka topic named customer. Then to define the schema of this customer Kafka topic, I will go to Kafka model module and create a new Auro schema file, customer AVSC. Here I will define the namespace, which is the Java package name, and set the class name as customer Auro model. I will keep the fields as simple, and I will have ID, UUID, and 3 string fields for customer username, first name, and last name. Now, if I run Maven install commands in Kafka model module, the Auro Maven plugin will create the customer Auro model class for me. As you see, the new Auro model is created for customer here. Great, now I will create the modules in the customer service. Here, instead of having the single Spring Boot application class, I will move this to a customer container module and create the other modules. Let's create customer container Maven module first. I will choose customer service as the parent here. Then I will move the customer service application class into this new module with the same package name. Now, in the customer service application class, as in the other services, like in order service Spring Boot main class, I will enable JPA repositories and entity scan annotations with the base packages property. I will use customer package here. Remember that these annotations are necessary when you have JPA repository and entities in different modules. I will also move the application YAML and the init schema and init data SQL files. In the application YAML, I will add the Kafka topic name using customer service, customer topic name property. Remember that Kafka topic name is customer. In the application YAML, I will add the Kafka and Kafka producer configuration, as in the order service, because now I will publish an event into Kafka from customer service. I don't need Kafka consumer config here because I will not consume any Kafka topic. Instead, I will publish customer data into Kafka and let the order service to consume that customer data and update its database eventually. Please note that all these configurations that I wrote in the application YAML files of each service can actually be managed and pulled from a config server. In this course, I focus on the architectural design and the patterns such as Saga, Outbox, and CQRS. However, if you want to apply the externalized configuration pattern and use a config server using Spring Cloud, you may want to check my other course, Event-Driven Microservices, Spring Boot, Kafka, and Elasticsearch. In that course, you will find the implementation details of config server, along with the most of the Spring Cloud stack. Here, I will not change the init schema and data SQL files. However, note that you can actually remove this materialized view definition because I will not use it from the order service. Instead, I will create a duplicate table in the order service using CQRS pattern. Then I will delete the source folder in the customer service. And be sure that the PAM XML file has the packaging PAM property for the parent customer service. I will also get the dependencies and Spring Boot Maven plugin to the new modules PAM XML file, and only keep the Spring Boot starter dependency for now. Now I will create the other Maven modules. First, customer application. Then customer data access. Hi everyone. In this section, I will make a quick enabling and running Kubernetes, automating software deployment. Hi everyone. Let's run Kafka command to install Helm on my Mac machine. Please install it according to your operating system. Hi everyone. In this lecture, Hi everyone. Let's start creating one with you. All right. run these commands successfully before continue with the rest of the lecture. Now I need this. I will run gcloud out login just to be sure I am logged into. Check documentation on the food ordering system base directory, then your Docker images will be created. Correctly for Google Artifactory, tagging the local image section, I see that I need the location, project, repository, and image. Europe West 4 repository. So I will run commands gcloud out configure docker Europe West 4 docker package dev. And update my config.json file for Docker with this command, as you see here. Service from the Docker images location, which is the region that I chose for the artifact registry. Then I will set the project name after a /. You can get your default project name using gcloud config get project command. Then I will add a / and then use food ordering system repository, which is the name of the repository on Google Cloud Artifactory. And then I set the Docker image name with version 10 snapshot. With this command, I will tag my Docker images using the Google Cloud location, project name, and repository values. Now I will run same Docker tag command for all services, for customer service, payment service, and restaurant service. Then I will check Docker images command again to see if all 4 images are tagged correctly. Now I will push these tagged Docker images to Google Artifactory. For this, I will run Docker push command and simply pass the tagged Docker image name. Here I push the restaurant service Docker image. Similarly, I will push the other tagged Docker images for all of the services. Now let's go and check the Google Artifactory in Web Console. As you see, my Docker images are pushed to the food ordering system repository Artifactory. For the Docker tag and push commands, I will create an executable file to tag and push commands. I will also add gcloud alt login to the beginning of this file. For the version, I will use $1, so it will be the first argument to this executable file, so that I make the version as a parameter to this file. Whenever a new version is released, I can simply call this file to tag and push a new Docker image using the new version as the parameter. All right, so I am ready to deploy and run my server. Hi everyone. In this lecture, I will create a performance test using JMeter. This property actually defines the number of threads that will be created in the Spring Kafka listener, as you see here in the config class. Since I have 3 partitions on my Kafka topics, on the consumer side, I can create 3 threads to consume each partition in parallel. But since I create 3 instances of each service, instead of having 3 threads in an instance of a service, I will create 1 thread per instance, but in total, I will have 3 consumer threads running in different service instances. Since all instances will share the same consumer group, in the end, 3 partitions will be distributed to the instances of the service so that each instance will consume a single partition of a Kafka topic. Now for the order service application 2, I set the port as 8182 and set concurrency level 1. And also here I will set Spring SQL init mode to never, because I have a schema initialization SQL as you see here in the order service resources folder, and I just want to do the initialization in a single instance. Otherwise, all 3 instances will start creating the schema at the same time, and it will create a race condition issue, as all will be working at the same time. For the third service, I have the same VM parameters, but I changed the port as 8183. Similarly, I have 3 payment service applications. Similarly, I have 3 payment service applications here. Since I don't have a REST API, I will just set the concurrency level to 1 in each application instance without setting any port. And also I set the init mode to never for instances 2 and 3. And finally, for the restaurant service, I have 3 instances, and for each of them I set the concurrency level to 1 and set the SQL init mode to never to instances 2 and 3. Great. I will increase the max heap of IntelliJ to be able to run all these services without an internal memory issue in IntelliJ. So I will go to help and change memory settings and use 4 GB instead of default 2. Depending on your machine configuration, you may choose more than 4 GB also in IntelliJ if you see a slowness. Now I can run startup shell script first. After checking the containers with Docker PS command, let's also check the Debezium connectors through Postman. As you see, all 4 connectors are created. Now I will run all instances of each service. It is not that I run only one instance for customer service, as it is not included in the Outbox pattern implementation. Before running the services, I will go to the payment container in its data SQL file and set this customer's credit to 50,000. I will adjust the history data as well to be consistent, so 70,000 credit and 20,000 debit. Then I will go to init data SQL file of restaurant service and set this product price to 1. So I will be able to send 50,000 order for this product using the customer with credit of 50,000. I will use this customer and product information for the load test. All right, let's run all instances of our services. I can choose all of them and start them at the same time in the IntelliJ. Oh, I got an error in the order service here. The port should be 8181 for the first instance instead of 8182, so I'll change it. Let's rerun the services again. Great, let's first test these instances in Postman. I will create a customer on Customer API on port 8184. Then I will create an order using order services first instance on port 8181. I will adjust the price as 1 since we updated it in the init data SQL file. Now, if I check the order with tracking ID, I will see that it is approved. Then I will create another order using the second instance, which is running on port 8182. And let's create another one using the third instance, which is running on 8183. Again, if I check the order status with tracking ID, I will see that they are all approved. Now I will install JMeter to run multiple concurrent order requests. For my Mac machine, I will simply use brew install JMeter command. For Windows and Linux, you can install the binary version from the JMeter download site, and then run the executable inside the downloaded folder. For example, for Windows, it has a JMeter batch file to start JMeter. Now I will start JMeter. And first create a test plan with name food ordering system load test. And then create a thread group here.